What if I told you that the most dangerous part of a solar cycle isn't the peak, but the decline? That the real threat emerges not when the sun is throwing its biggest tantrums, but when it's supposedly calming down. In January 2026, a magnitude 6.4 earthquake struck Indonesia within hours of a moderate geomagnetic storm. Coincidence? Almost certainly, except similar patterns keep appearing in the data, whispering uncomfortable questions about connections we don't fully understand. The sun is entering its declining phase right now, and instead of quieting, it's broadcasting chaos through coronal holes that refuse to close. Stay until the end to discover why this year might challenge everything. You'll want to subscribe and stay with us as we venture into territory other channels won't explore. Because what's developing above our heads involves correlations and anomalies that challenge conventional narratives. The data exists, the patterns persist, but the explanations remain frustratingly incomplete or conveniently ignored. The sun is supposed to be calming down right now. That's what the textbooks say. That's what the models predict. Solar Cycle 25 reached its maximum sometime in 2024, and now, as we settle into 2026, we should be watching the sun's fury gradually subside like a storm losing steam. Sunspot counts should be dropping. Flares should be fewer. The magnetic chaos that defines solar maximum should be fading into the background hum of our star's 11-year heartbeat. But here's the problem. The sun didn't get the memo. Instead of retreating into quiet predictability, our star is throwing curveballs that have space weather forecasters scratching their heads and infrastructure managers losing sleep. Welcome to 2026, the year the declining phase decided to stop playing by the rules. You need to understand something fundamental about how we think about solar cycles. For over a century, astronomers have tracked the sun's activity by counting sunspots, those dark blemishes that mark regions of intense magnetic turmoil. The logic is simple. More sunspots mean more activity. Fewer sunspots mean less. Solar maximum brings the chaos. Solar minimum brings the calm. The declining phase, which we're entering right now, is supposed to be the gentle slope down from the peak, a multi-year cooldown, where the sun catches its breath before the next cycle begins. Except, that's not what's happening. Right now, as you're hearing these words, Earth's magnetosphere is getting pummeled by high-speed solar wind streams that have nothing to do with traditional sunspot activity. These streams are roaring out of massive coronal holes, dark regions in the sun's atmosphere that act like broken windows in a cosmic house, letting solar plasma escape at speeds exceeding 700 kilometers per second. Let me paint you a picture of what this looks like in real time. In late 2024, a sunspot called Active Region 3451 grew to monstrous proportions, larger than Jupiter, and proceeded to unleash a barrage of X-class flares, the most powerful category we measure. One of these flares, an X 5.1 event, sent a shockwave through Earth's ionosphere so intense that radio communications went dark across Africa and Europe for nearly an hour. Pilots reported GPS errors. Ships lost high-frequency contact. The Aurora Borealis danced as far south as Northern California. But here's what should unsettle you. That sunspot has long since rotated away, dissolved back into the solar surface. The flares have stopped. The sunspot count has indeed started to decline, just like it's supposed to. And yet, the geomagnetic disturbances haven't stopped. They've persisted, evolved, changed character. What's replacing the sunspot drama is something subtler, but potentially more insidious. Coronal holes, those gaps in the sun's magnetic canopy, have become dominant players. Unlike sunspots, which come and go with the cycle, coronal holes can persist for months, even years, especially during the declining phase. They're not explosive like flares. They don't announce themselves with dramatic bursts of radiation. Instead, they pour out steady, relentless streams of fast solar wind that slam into Earth's magnetic field like ocean waves against a seawall, over and over, wearing down our defenses through sheer persistence. And in the first weeks of 2026, we're seeing exactly this pattern. NOAA's Space Weather Prediction Center has issued multiple G1 and G2 geomagnetic storm alerts, not because of flares, but because of these high-speed streams. The aurora has been visible in places it has no business showing up: Minnesota, Montana, even parts of Scotland and Denmark. The current data tells a story that doesn't fit the neat narrative of decline. Solar wind speeds have been hovering between 400 and 600 kilometers per second for weeks, with periodic spikes above 700. The Planetary K index, which measures global geomagnetic activity, has been dancing between 3 and 5, indicating unsettled to active conditions. These aren't catastrophic numbers, not yet, but they're persistent, they're chronic, and they're happening when we're supposed to be entering the quiet years. It's like watching a fever that won't break, a patient who should be recovering, but keeps spiking temperatures. Now, before you dismiss this as mere scientific curiosity, something pretty to photograph but ultimately harmless, let me connect the dots to your daily life. Every time a high-speed solar wind stream compresses Earth's magnetosphere, invisible currents are induced in the ground beneath your feet and in the metal structures we've built above them. Satellites in low Earth orbit experience increased drag as our atmosphere heats and expands. GPS signals scatter and drift. Power grids, especially those at high latitudes, feel phantom currents flowing through their transformers. These aren't theoretical risks. They're documented effects happening right now, every time the solar wind ramps up. The historical record gives us reason to pause. The Halloween storms of October 2003 occurred well into the declining phase of solar cycle 23, catching everyone off guard with their intensity. Those storms knocked out satellites, scrambled GPS, and damaged transformers in Sweden and South Africa. The point isn't that 2003 was worse than now. The point is that declining phases aren't safe. They're unpredictable. They can harbor surprises that peak solar activity never delivered. But here's where things get interesting, where the official story starts to crack at the edges and let in some uncomfortable questions. What if this unexpected persistence of solar activity isn't random at all? What if there are patterns, cycles within cycles, influences we haven't fully mapped? Some researchers, operating at the fringes of mainstream solar physics, have begun asking whether planetary positions might play a role in modulating solar behavior. The idea sounds wild, almost astrological, until you remember that the sun isn't an isolated ball of fire. It's embedded in a complex system of magnetic fields, charged particles, and resonances that extend throughout the solar system. What makes 2026 particularly unnerving is not just what we're seeing, but what it might foreshadow. We're entering uncharted territory, not because the sun is doing something it's never done before, but because our dependence on vulnerable infrastructure has never been greater. In 1959, when a major storm hit during a declining phase, it knocked out telegraph systems. Inconvenient, sure, but civilization didn't grind to a halt. In 2026, a similar event would take out satellites, GPS, power grids, internet backbones, financial networks. The world has changed. Our exposure has exploded. So as you settle into this year, remember this. Somewhere above your head, invisible streams of charged particles are racing toward Earth at speeds that would cross the distance from here to the moon in less than an hour. And when they arrive, when they slam into the magnetic bubble protecting us, they'll squeeze it, shake it, and send ripples through every conducting material on the planet. Most of the time, our technology will shrug it off. But every once in a while, something breaks. And we're entering a phase where those breaks might come more often than anyone is prepared to admit. Imagine the sun's atmosphere as a magnetic quilt, woven from invisible field lines that loop and twist above the surface. Now imagine someone cutting holes in that quilt, creating gaps where the fabric simply vanishes. That's essentially what coronal holes are. Regions where the sun's magnetic field opens up to space instead of looping back down, creating escape hatches for solar plasma. Unlike the bright, chaotic regions around sunspots, coronal holes appear dark in ultraviolet and X-ray images, not because they're cooler, but because they're emptier. The plasma that should be there has already left, streaming outward at ridiculous speeds, racing toward the planets like a cosmic wind tunnel. The physics behind these structures is deceptively simple. Magnetic field lines on the sun usually form closed loops, arcing from one magnetic pole region back to another, trapping hot plasma in elegant structures we see as coronal loops. But in coronal holes, the field lines are open, stretching out into interplanetary space without looping back. This open geometry creates a highway for solar wind to escape, and because the plasma isn't trapped, it accelerates to much higher speeds than the ambient solar wind. Where normal solar wind might cruise along at around 300 kilometers per second, the wind from coronal holes regularly exceeds 600, sometimes pushing toward 800. What makes coronal holes particularly relevant to 2026 is their behavior during the solar cycle. During solar maximum, when the sun's magnetic field is at its most chaotic, coronal holes tend to be smaller, more confined to the polar regions. But as the cycle declines, as the sun's magnetic field begins to reorganize itself, coronal holes grow larger and migrate toward the equator. This means they start pointing directly at Earth. A massive coronal hole near the sun's equator can send high-speed streams our way for days or even weeks as the sun rotates, creating a recurring pattern of geomagnetic disturbances roughly every 27 days. Recent observations have documented exactly this pattern. In December 2025, a coronal hole spanning over 30% of the visible solar disk rotated into Earth-facing position, and for nearly a week, we got hammered by solar wind exceeding 650 kilometers per second. No AA issued G2 storm warnings. Aurora photographers scrambled to high-latitude locations. And then, 27 days later, the same coronal hole came back around, slightly evolved but still there, still pumping out fast wind. This is called a co-rotating interaction region, and it's one of the dominant space weather phenomena during declining phases. Let me translate what this means for the technology we depend on. Satellites in low Earth orbit operate in an environment called the thermosphere, which is absurdly thin by sea level standards, but dense enough to create drag. When a high-speed solar wind stream compresses Earth's magnetosphere, it pumps energy into the upper atmosphere, heating it and causing it to expand. This expansion increases atmospheric density at satellite altitudes, which increases drag, which requires satellites to fire their thrusters more frequently to maintain orbit. Each thruster burn consumes precious fuel that's finite. Over time, repeated storms can significantly shorten a satellite's operational lifetime. GPS accuracy takes a hit through multiple mechanisms. The ionosphere, that electrically charged layer of atmosphere between about 80 and 1,000 kilometers altitude, becomes turbulent during geomagnetic storms. GPS signals have to pass through this layer, and when it's churning with enhanced electron density and irregularities, the signal path gets distorted. Your phone might think you're 50 meters from where you actually are. For most civilian applications, that's annoying but survivable. For aircraft landing in poor visibility, for maritime navigation in coastal waters, for precision agriculture and autonomous vehicles, that error margin is unacceptable. Power grids face a more insidious threat. When geomagnetic storms disturb Earth's magnetic field, they create time-varying magnetic fields that induce electrical currents in any long conductor, like power lines. These geomagnetically induced currents flow into the grid infrastructure, particularly affecting transformers. The currents aren't huge by power grid standards, but they're direct current, and transformers are designed for alternating current. DC current in a transformer causes the magnetic core to saturate, heating up, generating harmonics, and in extreme cases, permanently damaging the transformer windings. The chronology of recent events reads like a slow-building disaster movie. In late January 2026, a coronal hole stream triggered a G1 storm that expanded to G2 within hours. Aurora were reported from northern Michigan and Maine. A commercial airline flying the transpolar route experienced GPS errors that forced manual navigation for 3 hours. In early February, another stream arrived, this one faster, peaking at 720 kilometers per second. Power grid operators in Scandinavia reported GIC levels approaching their alert thresholds. Satellite operators logged increased drag and orbital decay rates. But here's what really should keep you up at night. These are the effects we can measure, the disruptions to systems we've instrumented and monitored. What about the effects we can't measure yet? The subtle interactions between solar wind and Earth's environment that we haven't mapped because we didn't know to look. Every geomagnetic storm injects enormous amounts of energy into Earth's magnetosphere and upper atmosphere. Some of it lights up the aurora. Some of it heats the thermosphere. But could some of it couple into systems we haven't considered, into the Earth itself, into geological processes that operate on completely different timescales? So, as you think about 2026, remember that the sun is broadcasting streams of charged particles toward us almost continuously now, not in dramatic bursts from flares, but in steady, powerful flows from holes in its magnetic atmosphere. These streams are invisible. They make no sound. They trigger no alarms in your phone. But they're real. They're impacting our technology in measurable ways, and they're showing no signs of letting up. The modern world runs on invisible threads. GPS signals bouncing from satellites 20,000 kilometers overhead tell your phone where you are. Power lines stretching across continents deliver electricity from distant generators to your home. Radio waves refracted through the ionosphere connect ships, planes, and remote stations. And all of it, every single thread, is vulnerable to something most people never think about: the weather in space. Let's start with satellites, because they're the most obviously exposed. Anything orbiting below about 1,000 kilometers altitude lives in low Earth orbit, and LEO is not empty space. It's still technically part of Earth's atmosphere, just an absurdly thin part. At 400 kilometers, where the International Space Station orbits, atmospheric density is about 1/1,000,000th of what it is at sea level. That sounds like nothing, and for most purposes, it is nothing. But when you're moving at 8 kilometers per second, even near nothing creates drag. And when a geomagnetic storm hits, that near nothing becomes significantly more. The thermosphere heats up, expands outward, and suddenly satellites are plowing through air that's 10 times denser than normal. The global positioning system depends on you receiving signals from at least 4 satellites simultaneously, measuring the tiny time differences in those signals to triangulate your position. The precision is absurd. We're talking about timing differences measured in billionths of a second, translated into positioning accuracy measured in meters. But geomagnetic storms break all 3 key assumptions. Satellite orbits shift slightly due to increased drag. Onboard atomic clocks experience subtle radiation effects. And most importantly, the ionosphere becomes wildly unpredictable during storms. Aircraft navigating by GPS experience sudden position jumps that confuse autopilot systems. The FAA has documented hundreds of GPS anomaly reports from commercial aviation during moderate geomagnetic storms. Maritime shipping faces similar issues in coastal waters where precise positioning is critical. Agricultural equipment using GPS for precision planting can end up off track. And the autonomous vehicle industry, betting everything on centimeter-level GPS accuracy, has to reckon with the fact that during space weather events, that accuracy simply evaporates. Power grids occupy a special place in the infrastructure vulnerability hierarchy, because they're both critical and fragile. Earth's magnetic field, normally stable, starts fluctuating during a storm as the solar wind buffets the magnetosphere. These fluctuations induce electric fields in the ground, which drive currents through power lines. The currents flow through the grid looking for the path of least resistance, often through large transformers. And transformers hate DC current. The March 1989. Quebec blackout remains the canonical case study. A moderate G4 geomagnetic storm triggered a sequence of transformer trips that cascaded through the Hydro-Quebec system in 90 seconds. 6 million people lost power for 9 hours. Some parts of the grid took days to restore. And that storm was smaller than what we might face in 2026. Power grids have gotten more interconnected, more complex, more optimized for efficiency rather than resilience since 1989. Financial infrastructure introduces another layer of concern. High-frequency trading, electronic funds transfers, and time-stamping of financial transactions all depend on precise time synchronization, usually provided by GPS. When GPS timing goes wonky during a geomagnetic storm, financial systems can experience synchronization errors that cascade into trading anomalies. In 2012, a GPS timing error of just 13 microseconds contributed to a trading glitch that cost Knight Capital $450 million. During a strong geomagnetic storm, GPS timing errors can be orders of magnitude larger. Radio communications, particularly in high-frequency bands, become unreliable during geomagnetic storms. The ionosphere, which normally reflects HF radio waves allowing over-the-horizon communication, becomes turbulent and absorptive. Military communications that depend on HF as a satellite backup discover there is no backup. Aviation over polar routes loses contact with ground stations. Maritime vessels in remote oceans can't call for help. The X5.1 flare from late 2024 provides a recent example. The flare lasted about 30 minutes, but the radio blackout it triggered persisted for over an hour across the entire sunlit hemisphere. Pilots over Africa reported complete loss of HF communications. European air traffic control had to route flights around affected areas. Ships switched to satellite backup, which worked until the satellites themselves started experiencing anomalies. But these are all acute events. What worries specialists more is chronic degradation, the slow accumulation of damage from repeated moderate storms. Transformers stressed by geomagnetically induced currents don't fail immediately. They age faster, developing hotspots, insulation damage. Years later, they fail during routine conditions, and nobody connects the failure back to the storms that weaken them. Satellites accumulate radiation damage. GPS clocks drift slightly more each storm. The infrastructure doesn't collapse, it just gets more fragile. Space weather forecasting has improved dramatically, but it still can't give us the precision we need. No AA can tell us when a high-speed stream is heading toward Earth, usually with several hours or days of warning. But what they can't tell us with certainty is how strong the resulting geomagnetic storm will be, because that depends on the magnetic field orientation in the solar wind. We can only measure that at the L1 monitoring satellite, about 90 minutes of solar wind travel time from Earth. Not enough time to shut down vulnerable grid sections. Not enough time to reorient critical satellites. So here we are in 2026, riding a technological infrastructure that was designed for calm space weather, operated at the edge of its safety margins, and now being tested by a sun that refuses to follow the script. The declining phase was supposed to give us breathing room. Instead, it's giving us a steady drumbeat of moderate storms that stress everything simultaneously. That's the knife edge we're balanced on. Now we're going to wade into controversial territory, into ideas that make mainstream scientists uncomfortable and fringe theorists excited. The question is simple enough. Can solar activity trigger earthquakes? The official answer, delivered with confident certainty by geophysicists, is no. Earthquakes are driven by plate tectonics, by the slow grinding of continental plates powered by convection in Earth's mantle. Solar storms might mess with our satellites, but they don't move mountains. That's the consensus. But consensus has been wrong before. Plate tectonics is real, well documented, and explains the vast majority of seismic activity. Stress accumulates along fault lines as plates push against each other. Eventually, that stress exceeds the friction holding the plates in place, and they slip, releasing energy as an earthquake. This is not controversial, but the timing of when a fault decides to slip, when a system that's already under critical stress finally lets go, might be influenced by external triggers. A series of peer-reviewed studies over the last 2 decades have reported statistical correlations between solar wind parameters and seismic activity. A 2013 paper found a correlation between high-speed solar wind streams and increased earthquake frequency in certain regions. A 2016 study reported correlations between proton density in the solar wind and large earthquakes occurring within specific time windows. These aren't fringe publications. They're appearing in legitimate journals. The correlations aren't perfect. They're statistical, but they're there, persistent enough that they can't be dismissed as pure coincidence without explanation. One hypothesis involves the reverse piezoelectric effect. Piezoelectric materials generate electrical voltage when mechanically stressed. The reverse effect is that applying voltage causes them to mechanically deform. Earth's crust contains massive amounts of quartz-bearing rock. During geomagnetic storms, electrical currents are induced in the ground. Could these currents, flowing through quartz-rich rock, cause subtle mechanical stresses? Could those stresses be enough to nudge a fault that's already critically loaded toward failure? Critics point out that the energy involved in geomagnetically induced currents is trivial compared to tectonic forces. They're right about the energy budget, but they might be wrong about what matters. In systems poised at critical thresholds, tiny triggers can produce large effects. A single snowflake doesn't weigh much, but it can trigger an avalanche. The question isn't whether solar wind can generate tectonic scale forces. The question is whether it can provide the tiny extra nudge that releases forces already there. Other researchers have looked at correlations between geomagnetic field variations and subsequent seismicity, finding patterns that suggest Earth's magnetic field disturbances precede earthquakes by hours or days. The mechanism is even more unclear. One hypothesis involves electromagnetic coupling between the ionosphere and the lithosphere. Another suggests that solar wind might influence Earth's rotation rate in ways too subtle to measure directly, but significant enough to affect fluid dynamics in the outer core. To be absolutely clear, there are also studies showing no significant correlation after rigorous statistical filtering. A 2018 analysis concluded that apparent correlations disappeared when you properly controlled for the frequency of both phenomena. So we're left in an uncomfortable place where the data is contested, the mechanisms are unclear, and the scientific community is deeply divided. Let's look at specific cases. The magnitude 9.1 Tohoku earthquake in March 2011 occurred during elevated solar wind. The magnitude 6.4 Indonesia earthquake in January 2026 occurred within 24 hours of a G2 geomagnetic storm. Are these coincidences? Almost certainly. But statistical studies analyzing decades of data across thousands of events are finding patterns that deserve investigation. The viewer takeaway should be epistemic humility. We know a lot about earthquakes. We know a lot about solar storms. But we don't know everything. The Earth is complex. The Sun is turbulent. The interaction between them might have subtleties we haven't discovered yet. Dismissing the possibility requires being certain our models are complete, and that's dangerous certainty given how often science has been surprised. Whether or not solar activity causes earthquakes in any meaningful sense, the perception of danger in 2026 is amplified by uncertainty itself. If Earth's systems are sensitive to solar influences in ways we don't fully understand, then our ability to predict or mitigate risks is compromised. That uncertainty creates space for both legitimate scientific questions and wild speculation to coexist. Welcome to the frontier. Space is getting crowded, not the dramatic, science fiction kind of crowded, but the real kind, where thousands of satellites occupy the same narrow shells of altitude, where defunct rocket bodies drift alongside active spacecraft, where collision avoidance has become a daily operational reality. And right now, in 2026, as the sun continues its atmospheric assault, that crowding problem is accelerating toward crisis. As of early 2026, there are approximately 9,000 active satellites in low Earth orbit, with thousands more defunct satellites and debris fragments large enough to track. The majority orbit between about 300 and 1,000 kilometers altitude. At these altitudes, atmospheric drag is the dominant force determining orbital lifetime. Under normal solar conditions, drag is predictable. But we're not in normal conditions. We're in an extended period of elevated solar wind activity, keeping the thermosphere hotter and denser than models predicted. Solar wind energy gets deposited into Earth's upper atmosphere through complex interactions. The energy heats the thermosphere, causing it to expand upward. At satellite altitudes, this expansion can increase atmospheric density by factors of 2, 5, even 10 during strong storms. Drag force is proportional to density, so a 10-fold density increase means 10-fold drag. Satellites that were comfortably maintaining orbit suddenly find themselves losing altitude faster than planned. They burn propellant to compensate, and if storms keep coming, they keep burning propellant until they run out. The current situation is unprecedented, not because we haven't seen geomagnetic storms before, but because we've never had this many satellites in orbit during an active solar period. The satellite megaconstellations deployed for global internet coverage were designed during solar minimum. Their propellant budgets assumed a certain baseline drag environment. That environment no longer exists. Reports indicate orbit maintenance propellant consumption is running 20 to 30% higher than projected. Some satellites won't make it to their planned deorbiting dates. They'll run out of fuel, become uncontrollable, and turn into debris. The debris problem compounds exponentially through the Kessler syndrome. As debris density increases, collisions become more likely. Each collision creates more debris, increasing collision probability further. At some critical density threshold, the cascade becomes self-sustaining, rendering entire orbital shells unusable for decades. We're not at that threshold yet, but we're closer than ever, and atmospheric drag acting as natural cleanup becomes less effective when the atmosphere itself is being pushed around by solar storms. GPS constellation stress tells a more specific story. GPS satellites orbit at about 20,000 kilometers in medium Earth orbit. At this altitude, atmospheric drag is negligible, but radiation exposure is intense. MEO satellites sit inside Earth's radiation belts, where charged particles from solar storms get trapped and spiral back and forth. During active solar periods, these belts get energized, particle fluxes increase, and radiation doses climb. Onboard computers experience bit flips. Solar panels degrade faster. Those precise atomic clocks can experience timing jitter from radiation effects. Space weather prediction becomes acute when we consider how little warning we have. The DSCO VR satellite at L1 sits about 90 minutes of solar wind travel time from Earth. It measures the solar wind and sends data back, giving us a snapshot of what's about to hit us. But 90 minutes isn't enough time to move satellites, reconfigure power grids, or do much beyond sending alerts. Human spaceflight adds urgency. The International Space Station orbits at about 420 kilometers, where atmospheric drag increases dramatically during storms. ISS has thrusters and gets regular boosts to maintain altitude, but during extended high solar activity, the station requires more frequent reboosts. More concerning is radiation exposure for the crew. During solar particle events, energetic protons can penetrate spacecraft shielding, delivering radiation doses that accumulate toward career limits. looking toward future missions, margins get tighter. NASA's Artemis program aims to return humans to the moon, which means spending time outside Earth's protective magnetosphere. Mars missions would require months or years in deep space. Solar particle events that are merely concerning for LEO operations become potentially lethal beyond the magnetosphere's protection. The satellite industry is responding with design changes and operational adaptations. Newer satellites carry more propellant margins, better radiation-hardened electronics, autonomous collision avoidance systems. But the existing constellation can't be retrofitted. They have the propellant they have, the shielding they have, the vulnerabilities they were launched with, and many are operating in an environment more hostile than designers anticipated. Insurance markets are starting to notice. Satellite insurance premiums have climbed as underwriters reassess risks based on actual space weather impacts. Some insurers are adding exclusions for losses attributable to solar activity beyond certain thresholds. When the money starts pulling back, when launching satellites becomes more expensive to insure, the economics shift. So here we are, operating the most complex orbital infrastructure in human history during a period when the environment is being constantly perturbed by an uncooperative sun. 2026 isn't bringing us a catastrophic orbital cascade. Not yet. But it's teaching us that the thresholds we thought we understood might be closer than we thought. Now, we're going to talk about something that makes most astronomers roll their eyes so hard you can hear it. The idea that planetary positions influence solar activity or terrestrial events in meaningful ways. It sounds like astrology. It feels like pseudoscience. And yet, buried in the dismissal and derision, there are small piles of data that don't quite fit the "it's all nonsense" narrative. Anomalies that suggest maybe, just maybe, we don't understand the solar system's electromagnetic environment as completely as we thought. This isn't about horoscopes or personality traits. This is about whether the massive magnetospheres of Jupiter and Saturn, the orbital resonances of Venus and Earth, the complex dance of the planets around the Sun, might interact with solar plasma dynamics in ways our models haven't captured. Let's start with the most respectable version of this idea, which is tidal force effects on the Sun. Jupiter and Saturn are enormous. Jupiter masses about 318 times Earth. Its magnetosphere is the largest structure in the solar system besides the Sun itself. When these planets align with each other, or with the Sun-Earth line, they create gravitational perturbations that, while tiny compared to the Sun's self-gravity, are real and measurable. Some researchers have proposed that these tidal forces might influence the Sun's internal dynamics, perhaps affecting the solar dynamo that generates magnetic fields, or the buoyancy of magnetic flux tubes that produce sunspots. The correlations claimed are weak and contested, but they exist in peer-reviewed literature. A 1990 paper by Charvatova claimed to find correlations between the Sun's motion around the solar system barycenter, driven by planetary positions, and solar cycle amplitudes. The mainstream objection is that the energy scales don't work. The gravitational influence of Jupiter on the Sun is about 6 orders of magnitude smaller than the Sun's self-gravity. It's not nothing, but it's close enough to nothing that invoking it to explain major solar phenomena seems desperate. Except, and this is crucial, we know the solar dynamo is a chaotic system operating near critical thresholds. Chaotic systems can be exquisitely sensitive to tiny perturbations. A butterfly flapping its wings doesn't power a hurricane, but it might influence when and where a hurricane that was going to form anyway actually develops. Could planetary positions be butterflies in the solar weather system? It's not impossible. It's just hard to prove or disprove with current data. The electromagnetic coupling hypothesis goes further, suggesting that what matters isn't gravity, but the complex interplay of magnetic fields and plasma flows. Jupiter's magnetosphere, driven by the planet's rapid rotation and internal dynamo, pumps out electromagnetic energy and charged particles. it creates a bow shock in the solar wind. It has magnetic field lines that stretch for millions of kilometers. Could these structures interact resonantly with solar magnetic activity? Could Venus, whipping around the sun every 225 days, create plasma wake patterns that feed back into solar surface flows? These ideas are speculative, pushing at the boundaries of plasma physics in regimes we can't easily test. But they're not pure fantasy. They're asking whether the solar system is more electromagnetically connected than our simplified models assume. Historical patterns provide the tantalizing bait that keeps these ideas alive. Some researchers claim to find correlations between grand planetary alignments, particularly of the gas giants, and peaks or valleys in solar cycle activity. The claim is that when Jupiter and Saturn align in certain ways, solar cycles tend to be stronger or weaker. The correlations are statistical, not predictive of individual events, and they fall apart under some analytical approaches while holding up under others. It's messy data producing messy conclusions, exactly the kind of situation where confirmation bias can run wild. Believers see patterns, skeptics see noise, and both sides can cite papers supporting their view. Let me be very clear about the astronomy here. The gravitational effect of planets on the sun is real, but tiny. The electromagnetic effects are speculative and poorly quantified. The resonance ideas are on the fringe of physics, invoking mechanisms that aren't well established. Most professional solar physicists dismiss all of this as numerology, as people finding patterns in random data because humans are pattern-finding machines. And they're probably right. The burden of proof is on the people claiming an effect, and that proof hasn't been delivered in a form that convinces the mainstream. But, and this is important, the mainstream has also been wrong before about interactions that seem too small to matter. Chaos theory, developed in the last half-century, taught us that tiny perturbations can have outsized effects in nonlinear systems. The sun is nothing if not a nonlinear system. Now, in 2026, are there notable planetary alignments happening? Let's check. Venus and Earth are in relatively close conjunction in early 2026, though they're always relatively close in astronomical terms. Jupiter and Saturn, which had a great conjunction in late 2020, are now spreading apart in their orbits. There's no dramatic grand alignment of all the planets, nothing that jumps out as astronomically unique. But if you squint, if you look at the orbital positions through the lens of someone trying to find patterns, you can construct narratives about resonances and angular relationships. This is the danger zone, where pattern seeking becomes pattern imposing. We have to be ruthlessly honest about whether we're discovering something real or constructing something convenient. The cosmic coincidence narrative appeals to a deep human need to find order in chaos, to believe that the universe operates according to discoverable rhythms rather than random fluctuations. Ancient cultures built entire worldviews around planetary movements, encoded astronomical cycles into architecture and calendars, treated the sky as a clockwork mechanism whose patterns governed earthly affairs. We've inherited that pattern-seeking instinct even as we've developed scientific methods to test whether the patterns are real. And sometimes the patterns are real. Milankovitch cycles, the periodic variations in Earth's orbit, and axial tilt that drive ice age cycles are absolutely real and absolutely caused by planetary gravitational interactions over tens of thousands of years. So planetary positions can matter. The question is whether they matter at timescales and magnitudes relevant to solar cycle behavior. There's a broader theoretical framework here called solar inertial motion, which examines how the sun moves around the solar system barycenter, the center of mass of the entire system. Because Jupiter is so massive, the barycenter isn't at the sun's center. It's actually outside the sun's surface. The sun wobbles around this point in a complex pattern determined by all the planetary positions. Some researchers have claimed that the sun's velocity and acceleration in this motion correlate with solar cycle parameters. The mechanism would be that motion affects the solar dynamo, either through changes in angular momentum distribution or through some poorly understood interaction between rotation and magnetic field generation. It's plausible enough to study, weird enough to make most people skeptical. The morphic resonance angle, imported from Sheldrake's biological theories and adapted to solar-terrestrial physics by a very small number of people, suggests that systems can share states or information through fields that aren't mediated by the four fundamental forces. If you're a mainstream physicist, this is word salad, invoking non-existent fields to explain correlations that are probably coincidental. If you're exploring the edges of what physics might be missing, it's an intriguing hypothesis that deserves investigation, even if it's probably wrong. The honest position is somewhere in the middle. Acknowledge that we don't understand everything about how information propagates through complex systems. Remain open to discovering new physics, but demand rigorous evidence before accepting claims that violate everything we currently know. What should you, the viewer, take away from this planetary speculation? First, be skeptical of grand claims that planetary positions control solar or terrestrial events. The mainstream rejection of these ideas is based on solid physics and justified by the lack of convincing evidence. Second, remain curious about the possibility that our understanding of solar-planetary interactions is incomplete. Science advances by finding phenomena that don't fit existing models and then expanding the models. Third, distinguish between "this is an interesting correlation to investigate" and "this proves the theory." Correlation never proves causation, especially when you're looking at complex, noisy data. And fourth, recognize that pattern seeking can be both a powerful tool for discovery and a dangerous trap for self-deception. The human brain will find patterns even in pure randomness if you let it. The reason this matters for 2026 is that if planetary influences on solar activity are real and significant, then the unexpected persistence of high solar wind streams and geomagnetic activity during the declining phase might be explained by a planetary configuration that's modulating the sun's behavior. If they're not real, then we need different explanations for why this declining phase isn't behaving like previous ones. Either way, the question pushes us to look more carefully at the data, to challenge our assumptions, to admit that solar physics still has unsolved problems. And that's actually healthy, even if it's uncomfortable. The worst thing science can do is decide it has all the answers and stop asking questions. 2026 is forcing questions on us, whether we like it or not. We've spent 6 parts focused narrowly on the sun, on Earth, on the fragile technological web that connects them, and on speculative theories that challenge mainstream science. Now we need to zoom out, way out, to remember that all of this, the solar storms, the satellite constellations, the planetary positions, even the Earth itself, is a tiny subset of a universe that keeps revealing itself to be stranger and more magnificent than we imagined. Because while we've been worrying about geomagnetic indices and GPS timing errors, astronomers have been discovering things that make solar weather look quaint by comparison. And these discoveries matter, not because they directly affect 2026, but because they reshape how we think about our place in the cosmic story. Let's start with the Vera C. Rubin Observatory, which just began science operations in Chile and is already changing the game. This is a telescope designed to survey the entire visible southern sky every few nights, creating a constantly updating movie of the universe rather than a static snapshot. In its first months of operation, it discovered an asteroid designated 2025 VR7, a rock about half a kilometer across, spinning so fast it completes a rotation every 2.1 hours. That might not sound dramatic until you realize that asteroids spinning faster than about 2.2 hours tend to fly apart from centrifugal force. This thing is right at the edge of stability. a cosmic top wobbling at the edge of destruction. What makes it fascinating is that we didn't know asteroids like this existed in such numbers. Rubin found this one almost immediately, suggesting there are many more waiting to be cataloged, forcing us to rethink our models of small body dynamics. Then there's the runaway supermassive black hole, confirmed by James Webb Space Telescope observations in late 2025. This is a black hole with the mass of about 20 million suns, roughly the size of the one at the center of our own galaxy, except it's been ejected from its host galaxy and is now racing through intergalactic space at about 2 million miles per hour. The mechanism that could eject something so massive is mind-bending. It requires the merger of two supermassive black holes, whose gravitational wave emission had a preferential direction, creating a recoil kick that launched the merged black hole like a cosmic cannonball. This thing is now traveling alone through the void, carrying with it a small retinue of stars that couldn't escape its gravity. It's a rogue galaxy core, an orphaned cosmic titan, and it tells us that galaxy mergers can produce outcomes far more violent than we'd modeled. Galaxy formation in the early universe continues to confound expectations. Webb's deep field observations have revealed massive galaxy clusters existing less than 1 billion years after the Big Bang, structures that shouldn't have had time to form according to standard cosmological models. These aren't just early galaxies. They're huge, mature-looking systems with evolved stellar populations and strong gravitational lensing signatures, all existing at a time when the universe should have been too young for such complex structure. The observations are forcing cosmologists to reconsider fundamental assumptions about how quickly matter could collapse, how efficiently stars could form, and whether there are processes in the early universe we simply don't understand. It's deeply uncomfortable for a field that thought it had the broad strokes figured out. Artificial intelligence is weaving itself into astronomical discovery in ways that are accelerating the pace of research. Traditional astronomy involved humans examining images or spectra, looking for unusual features, a slow and labor-intensive process limited by human attention spans and pattern recognition abilities. Modern AI systems can process terabytes of data per night, identifying transient events like supernova, variable stars, or moving objects with superhuman speed and accuracy. The Zwicky Transient Facility, operating in California, now uses machine learning algorithms to filter noise and flag interesting events in real time, enabling rapid follow-up observations before the phenomenon fades. What used to take weeks now takes hours. What used to require teams of graduate students can be done by trained neural networks that never sleep. This intersection of AI and physics has been formalized with the launch of a new journal called Physical Review X Intelligence, dedicated to research that combines artificial intelligence methods with physical sciences. The inaugural issue included papers on using machine learning to discover new materials, predict protein structures, solve quantum many-body problems, and optimize fusion reactor designs. The implication is that AI isn't just a tool for analyzing existing data. It's becoming a partner in scientific discovery, capable of finding patterns and relationships that human intuition might miss, capable of exploring parameter spaces too large for traditional methods. And this revolution is spilling into space weather forecasting, where neural networks are being trained to predict geomagnetic storm intensity from solar wind data with accuracy that approaches or exceeds traditional physics-based models. How does this connect back to our story about 2026 and solar danger? In multiple ways. First, better data processing means earlier detection of solar phenomena. Coronal holes can be identified and tracked automatically. High-speed stream arrival times can be predicted with machine learning models that learn from decades of data. The window of warning we have for space weather events is expanding because AI can process satellite observations faster than human analysts. Second, the tools being developed for one domain often transfer to others. Techniques developed for finding faint supernovae get adapted to detect subtle signatures in magnetometer data that might precede geomagnetic storms. Third, and most fundamentally, the acceleration of discovery across all scientific domains creates a feedback loop where our understanding of complex systems like the sun improves rapidly, even as those systems continue to surprise us. There's a philosophical dimension worth considering. We're living through a moment in history where the pace of cosmic discovery is faster than human culture can absorb. New black holes, new asteroids, new galaxies, new mysteries appear daily. The universe's weirdness budget keeps growing, and yet most people go about their lives barely aware of these discoveries, focused on terrestrial concerns that feel more immediate. The disconnect between cosmic reality and human perception has never been wider. We have the tools to peer deeper into space and time than ever before, to understand processes occurring billions of light years away or microseconds after the Big Bang, while simultaneously struggling to predict what our own star will do next week. The irony is profound. This broader cosmic perspective reframes the solar activity of 2026 as a local problem, a neighborhood weather disturbance in a universe filled with far more energetic and destructive phenomena. Compared to a gamma-ray burst that can sterilize a galaxy, or a supernova that outshines its entire host for weeks, or a supermassive black hole collision that radiates more power in gravitational waves than all the stars in the observable universe combined, our sun's occasional fits of activity are gentle and manageable. We're not facing cosmic annihilation. We're facing engineering challenges and infrastructure stress, problems that are solvable with enough will and resources. The danger is real, but not existential. The disruption is significant, but not civilization ending. Context matters. Yet the local matters precisely because we live here, because our technology depends on stable space weather, because the gap between what we can control and what the universe does to us remains vast. We've built a civilization that assumes the sun will behave within certain bounds, that satellites will keep working, that GPS will keep functioning, that power will keep flowing. Those assumptions held through most of human history when our technology was simpler and more resilient. They're being tested now, in 2026, as we push into an era where our capabilities and our vulnerabilities are both reaching unprecedented levels. The collision between cosmic unpredictability and human dependence on predictability is what makes this year dangerous. Not because the sun is doing anything unusual in cosmic terms, but because we've created systems that can't tolerate the sun being its natural chaotic self. The discoveries flowing from Rubin, Webb, and countless other instruments remind us that the universe doesn't care about our timelines or comfort levels. It operates according to physics that we're still learning, producing phenomena we didn't predict, challenging our models and our assumptions at every turn. Solar cycle. 25 declining phase acting up is just one small example of nature refusing to fit neatly into our categories. The early universe forming massive galaxies too quickly is another. A black hole getting kicked out of its galaxy is another. The pattern is clear. We don't have it all figured out. Not even close. And that's thrilling and terrifying in equal measure. So where does this leave us as 2026 unfolds? We're watching a sun that won't calm down politely, operating infrastructure that's more vulnerable than we'd like to admit, exploring theories that challenge conventional wisdom, and living in a universe that keeps proving it's more complex than our best models suggest. The danger isn't that we're helpless. We're not. We have forecasting systems, protective measures, contingency plans. The danger is that we might be complacent, assuming that because we've handled solar storms before, we'll handle them again, forgetting that the next big one could hit systems that didn't exist during previous events, or hit during a cascade of other failures, or exploit a vulnerability we haven't discovered yet. The proper response isn't panic, it's vigilance. It's continued investment in monitoring systems, in resilient infrastructure, in basic research that expands our understanding of solar-terrestrial interactions. It's acknowledging uncertainty while working to reduce it. It's asking hard questions about whether our technological choices are creating systemic vulnerabilities that a previous, less connected civilization didn't face. And it's maintaining perspective, remembering that while the sun can disrupt our satellites and power grids, it also provides the energy that makes life possible, drives our climate, and lights our days. The relationship between Earth and Sun is ancient, complex, and ultimately non-negotiable. We're along for the ride, trying to understand the driver, while also protecting ourselves from occasional swerves. The discoveries of 2025 and 2026, from runaway black holes to fast-spinning asteroids to unexpected solar activity, all point toward the same conclusion. The universe is not yet fully explained, and nature reserves the right to surprise us. The scientific endeavor is about reducing surprise through understanding, but it's also about maintaining humility in the face of complexity. We've learned an astonishing amount in the century and a half since we started systematically studying the sun. We've learned how stars work, how planets form, how galaxies evolve. But the learning never stops, because every answer generates new questions, and the frontier keeps expanding faster than we can map it. So keep watching the sky. Not with fear, though a little healthy respect for natural forces is warranted. Not with superstition, though the ancient impulse to see patterns and meaning in celestial events is deeply human. Watch with curiosity, with wonder, with the understanding that you're witnessing processes that have been unfolding for billions of years and will continue long after we're gone. The sun will keep cycling through its 11-year rhythm. Coronal holes will keep pumping out fast wind. Geomagnetic storms will keep shaking our magnetic field. And somewhere, in an observatory on a Chilean mountaintop, or a satellite at the L1 point, or a radio telescope array in the desert, someone will be watching, measuring, trying to understand just a little more than we did yesterday. That's the real story of 2026. Not that we're in danger, but that we're still learning. And learning in a universe this vast and strange is the most human thing we can do.